Dear students, welcome to the discussion of B trees. B trees are commonly used in databases and in the file systems for the reason that it provides a lot of A's in creating indexes. Especially when we are talking about large data sets, we need to have an organized or self-organized index. And we have seen the problems that we face while inserting and deleting records in the search tree. Hence, the advancements of handling the automatic building of or restructuring the tree when the record is inserted and deleted is taken care by the B trees, and that is why they are most commonly used. They provide efficient support for range queries and sequential access. This is the best part of using the B trees. It has various variants such as B plus trees, which are specifically designed for the use cases related to range and sequential access. Insertions in B trees are efficiently handled and deleted while maintaining the balance. And we will see how does it do that. When a node becomes full during an insertion, the node split occurs. And when the node becomes half or half full, or in the case of underflow of a node, the tree height is maintained or adjusts by balancing it. We are going to look in all these things in detail with this introduction. Let's get started on understanding how the B tree is created and how does it differ from the binary tree. As we have discussed in the earlier session that a binary tree looks like something similar given in the screen. Can you see my cursor? Yes, you can see my cursor. So let me take the laser pen. Yeah. So this is how the B tree looks like. A binary tree has this is how the binary tree looks like. Sorry. So the binary tree have root and edges. Each root have some values inside it, and each node can in turn have child nodes, and child nodes can have further their childs. Now, in such a case where a node can act as a parent to the level of nodes under it, and it can also act as a child node for the node above it. Now, if you see, this is one subtree inside this binary big tree. Here we have the height of the tree, which tells how many levels this tree has. Now, this tree is having, for example, for level, root level, then one, then two, and then three, and then four. So there are four levels. However, we see there are some roots that do not have, for example, this root or the node, sorry, this node doesn't have the child nodes. And you see, there are siblings at the same level, and these siblings are having their own children. Basically, it is trying to say that the binary tree can have some internal nodes without children and some internal nodes with more than one children. Basically, the childrens are not distributed in the binary tree in a uniform way, which causes the height of the tree to increase. And we do not see the binary tree as balanced tree at the end. We have also seen the situations wherein a binary tree can turn up to be skewed. Hence, there needs to be a way in which we can create or arrange the records in the index in a form of a balanced tree. And there comes the picture of or the concept of B trees. So you can consider the B tree as a balanced version of a binary tree which has certain rules. Now, if you look at this information, for example, here we have the binary tree and here we see the B tree. Now, if you look at their structure, the root is having more than one key, which is allowed in the B trees, and it is having some children, and all the childrens at the first level have equal number of children. For example, this node is having two children. this internal node is having again two children, and this internal node is having again two children. It is not a case wherein it is allowed to have unequal number of children. Okay, so this is how the balance is maintained. Now, when talking about B trees, there is one important factor which is called as the order of the tree. The order of the tree tells that how many children each node can have. For example, here the maximum number of children nodes can be 3. Okay, each node can have maximum of 3 children. And it can have, in this case, it is having 2. Okay, but if we have more values, then they can be 3 children. You see, this the root is having 3 children. Okay, similarly, this parent internal node 40 can also have one more children if there is an entry to come in the index. So the terms which are very important for us to remember is the order of the tree, which is given by P. So I want to underline this. So P is very important for us. When P is going to be 3, the number of keys will be P minus 1. The number of keys will be P minus 1. So, okay, let me just highlight this, that if P is 3, K is going to be 2. If P is 4, K is going to be 3, which means that the node can have 3 children, but each children is going to have how many keys? 2 keys. Okay, so this is the important thing. Okay, so in this slide, we have learned that the B trees are balanced version of binary trees, and the balance is maintained by following certain conditions. In order to understand those conditions, it is very important for us to understand some terms like order of the tree, keys inside each node, and the number of children each node can have. Now, B trees are balanced because all the leaf nodes, okay, all these nodes are called as leaf nodes, okay, all the leaf nodes are at the same level. But however, if you see here, this leaf node is at the level 2, but this node is at the level 6. Okay, so and that is why it is not balanced. So all the leaf nodes you see here in the B tree are placed in the same level. And the height of the tree is kept relatively small. You see the height is so lengthy and here the height is small. This balance is maintained through adjusting the nodes or adjusting the nodes. We will see how it is done. So these adjustments are done when you are inserting a value or inserting a key or inserting a node in the tree. Similarly for deleting. The balance is maintained through the adjustment during the insertions and the deletions. A very important thing is understanding the degree, also called as the order of the tree, which defines the maximum number of children a node can have, which is given by P. The number of keys inside each node is going to be P minus 1. Okay, so when you are asked in the exam to draw a binary tree, it is very important for you to understand what is the degree of the tree required, because based on the tree you will going to place the values inside each node. So the first thing is to know what is the degree of or the order of the tree. The number of keys inside a node is always one less than the number of children, and children is going to be equal to the number of P. For example, if P is 4, it means the order of degree is 4, which means that there can be 4 children placed under each parent node. The keys inside or the values inside each node is sorted, they are arranged. Okay, so let me take a pen. Okay, pen is here. So you see here, why is it not coming? A pen, ink, color. Okay, so you see here. Now here you see, for example, there are 2 values here given in the parent node, and they are in the ascending order. 22 is less than 60. Okay, so always the values or the keys inside a node is arranged in the ascending order. This is very important. Okay, the sorted keys are kept inside each node, which will allow us to efficiently search, uh, a node inside the B tree. Okay, so with this information, now let us understand the constraints or the rules of binary tree. There are one, two, three, four rules. This is the last rule is very easy. It says that each node has at most p tree pointers. What does it mean? It means that it has, three pointers maximum. These pointers are called as tree pointers because it creates, it is connecting a tree. That's why it is called as a tree pointer. So it is nothing but the number of children. Okay. Now, in each node, we are going to have a tree pointer and a data pointer. Okay. In each node, this is the structure of the node. In each node, we have a data pointer pointing to the data value and a tree pointer connecting a tree or a subtree inside it. Okay. And then the values are, again sorted like, the key 2 is greater than the key 1. For example, here we have 60. Let me make it cleaner. So, okay. So here we have two values, 22 and 60. They are sorted. So 22 will come first and 60. If you have another value, for example, 5 and for example, 2, then these are arranged as 2 and 5 as two different values inside a node. Okay, so this is how the internal keys are always kept sorted. Okay, so we are done with this also. Now, what does this say? This is the rule that we have also seen in the search tree, which says that the value of x, x is here, the values, data values. The value of x inside each subtree is going to, lie between the range of lower limit and the upper limit of the key of the node. For example, I will tell you here, this is the lower limit 5, 8 is the upper limit. Now the subtree inside it, in between, we are going to have the numbers which comes in the range of 5 and 8. So you see 6 and 7 lies between 5 and 8. So their values will be here. Okay. So this is the subtree. Okay. The values inside the subtree is going to always lie between the lower value of the node and the higher or the upper value inside the node. Okay, so for easy understanding, I'm saying it this one as a lower limit. This is the higher limit, and the tree, the subtree that will come, in between them is going to lie between them. It is going to lie between the lower and the upper limit. The left tree is always lesser than 5 in this case, okay, or this value. The right tree is always going to be greater than this number. Okay, for example, here 8. So we have the values in the subtree of this 8 as a right tree, always greater than 8, always greater than 8. Now here at this level, the node is having two values in the range of 9 and 12. So if there comes one more child to be, come here, so it will have the values less than, greater than or equal to 9, less than or equal to 12. Okay, for example, we can have 10 and 11 here. Okay, so did we understand this part? Okay. The values here, the values in the right tree is always going to be greater than this. For example, 9 and 12 always greater than 8. Okay. And the values here, the x values or the subtree is going to have values lesser than, 5. Okay. So we understood this. And then in middle, they are going to fall between the range of greater than 5 and less than 8 in this particular example. This is the B tree structure and B tree node structure. And this is one example. Okay, so let's move further. Okay, now let us understand how to draw a B tree. Okay, Now, when we have the values given to develop a B tree out of it, the first important thing, what we understand is we have to look at the order of the tree. Here, the order of the tree is 3. What does it mean? It means that it is going to have maximum children per node to be equal to 3. And the keys inside each node, is going to be 2. Maximum keys inside each node is going to be 2. Okay, so here, for example, we have values 5, 8, 1, 7, 3, 12, 9, 6 given in this insertion order. Okay, so as soon as you get this question, please write down these 2 important points. Okay, now let's start drawing this. Okay, so we have inserted 8. Okay, 8 is inserted. And then we insert 5. Okay, so I can insert it here or I can insert it here, but the rule says that the key 1 should be less than key 2. So we have inserted 5 like this. Okay, did you get this? Understood how, why they are 2? Because it can have 2 key values. Okay, now when we try to insert 1 here, okay, what will happen? Because the tree node can hold only 2 values, the node split should occur here. So there is a node split. Okay, so how does the node split? Now, first of all, I have to arrange 1, 5, 8. Now, what happens? This is my, node that will result, but I cannot have, I'm not allowed to put 3 values. So a node split should occur. So I will say 5, okay, and then 1 here, okay, and 8 here. Now, if you check the first rule says that the x, should be greater than its left child and lesser than to the right child. So my tree is 5, greater than my left child and lesser than my right child. Okay, good. So we are following it. We are following the rules. Okay. Now we have 7 to be inserted. So where will I insert 7? 7 is, less than, 7 is greater than 5. So I try to put it here. But you see, the leaf node should be filled before, adding anything into the root. When the leaf becomes full, then only we can add it into 5. So I'm not going to put 7 here. I will put 7 here. Okay, so we inserted 7. Okay, 7 is inserted. Now we are about to insert 3. So 3 is less than 5. I come to the left side, and then I am going to insert 3 here. Now you see, when I'm inserting, I'm taking care that my values are sorted. So 1 and 3, 7 and 8. Okay, so 1 here, 3 here, 7 here, and 8 here. Okay, so we have inserted 3 also. Now 12. Okay, now 12 is greater than 5, so I will have to insert it here. Okay, but I am not allowed to have 3 values inside it, so there will be a split, node split here. So node split. Okay, so how will the node split now? Okay, so it will be, now the new tree will look like this, 5. Okay, and then this node is splitted as 7, 8, and 12. The middle one will go to the root. So now I have 8 here. Okay, and now there are 2 values, 7, okay, and 12. Okay, so 7 is falling between 5 and 8. So this becomes the middle child. So I'm going to put 7 here and 12 as a right child of 8, because 12 is greater than 8, right? And then in the left child, I have, 1 and 3 unchanged. Okay, so we entered, we inserted 12 also. Now we want to insert 9. Okay, now I will try to insert 9. Where should 9 go? Should it come here? Should it come here or should it come here? It cannot come in the left or the middle because 9 is greater than 8. So it will ultimately come in the right child. So I have 9 and 12. Okay, 9 and 12. 9 inserted. Now 6. 6 cannot come as a left child. It can come between 5 and 8. So there is a place here. I can put 6 here. Okay. So if you see, this is our root node, 5 and 8. And this is the left child, and this is the middle child, 6 and 7. And this is the right child, 9 and 12. So this is how you create a binary tree. I hope you understood. Okay. Now I want you to draw it by yourself here. Okay. So we just practice here, right? I want you to draw here. Okay. Now, there is a very, nice tool available on the internet. You can check, if your answer is correct or not, or you can, have some random numbers and then create a B tree of it at this URL. Okay. So I will show you how this works. So let's open this. I'm opening the browser. So just it's opening. Okay, give me a minute. Okay. So V3, this is the URL that I gave you. Okay. So I have created a tree here, okay, which is having some values. And just give me a moment. Okay, so actually this is the, binary tree version, V tree version of the binary tree. Okay, so here, we were talking about this binary tree. Okay, so yeah, so this is the binary tree for the values, and this is the B tree for the same values. Okay, so now clear this. Okay, and let us insert some values or the values that we have just seen. Uh, let's insert these values. Okay. Okay, so what is the first value? Okay, let us take the degree as 3, and I'm going to insert the first number as 8, and then I click on insert. 8 is a node with a number 8 is created, and then we have a value 5, and then I click on insert. You see they are arranged. 5 is less than 8. Okay, so 5 will come first, K1, okay, less than K2, 5 and 8. And then we have a value 1, insert, okay. Because we have the maximum degree as 3, it can have only 2 values and the node split occurred and the middle value is taken as a root, and in the left we have a lesser value than the root, and in the right we have a value greater than the root. So we have 5 and 1 in the left child, 8 in the right child. Okay. So what is the third one now? 7. Let us insert 7. Okay. So now let's see how the 7 is inserted. It will check with the root, and then 7 is greater than 5. So it plays this as a right child. Okay. Now let us insert 3. So 3 is compared at the root, and then because it is less, it is sent to the left child. Okay. Now you see both the child nodes or the leaf nodes are full. If I try to insert any new node in the left child or the right child, the node split will occur. Okay. Now the next value, what we are trying to insert is 12. Okay. So I'm going to enter 12. 12 is greater than 5. It will send it to the right. So, and then in the right side, leaf node, we are going to have a node split. So you see, it will compare 5 and then 12 is inserted and the node split occurred, and then it sent the middle value of the leaf node as a root. Okay, then let's see, insert 9. Okay, insert 9. So 9 is greater than 8, and then it sent it to the right child. Okay. Now we have a place in the left child. We do not have place in the left leaf node. We do not have place in the right leaf node. If we are trying to put a value that comes in this range, then the node split will happen. However, if we are inserting something new value, which is falling in the range between 5 and 8, then we have one space or one value to be accommodated or can be accommodated in the middle child. So we have 6 now. Now tell me where this 6 will go. 6 will be checked at the node. 6 is falling in the middle. So it will send it to the middle node. And in the middle child, there is one space. Maximum I can have 2 values. Now I have only one value. So it will be accommodated without a node split. Done. So this is how, and the one that we drew just now, I removed it. Okay. So this is the one, right? Okay. So this is how it is done. Now, for example, if I want to delete a value, okay, let's see how the deletion is happening. You see, it deleted. Okay. Now, if I delete 3, okay, so let's see what happens. D. Okay. You see, the node is adjusted here. Okay. We will talk about deletion later. I'm just trying to give you a hint. For example, I'm trying to delete 7. Okay. You see some node adjustments are done to make sure that the height of the tree is maintained. If I delete 12, let's see what's happening. It's, yeah. And now if I try to delete 7, it says 7 is not available, so it cannot delete. Okay. Now, if I want to find a value, okay, for example, if I try to find 7, it will search at the root node and then go to the right and see it is falling between 8 and 9. It will not search the left tree because the value 7 is greater than 6. So it will skip checking it in the left side subtree directly. It comes to the right side. And then in the right side, it doesn't find. In the right side, it doesn't find the record, so it says not available. Now, for example, I try to search 10. 10 is also not available. Okay, if I want to print, the values printed are, again, let's see, what's it, how is it printing? 5, 6, 8, 9 in the arranged order. Okay, so if you want to clear, you can clear it and keep on checking and making some trees by yourself. Okay, but I want you to draw these, trees by yourself and check the result. I want you to draw here and I want you to draw this tree. Okay, pause the video, draw this tree and check. It should come like this. Okay, and here is one more example. Here is another example. Now, this is all about the insertions and how the adjustments are done in the binary tree. Okay, let us do this again together. This one.